My name is Taylor Leach, and this is Physics Lab 2. In this lab report, I will be going through Newton's second law and the momentum principle, as well as an analysis of paper's motion, a computational model similar to the paper's motion with only gravity as well as with gravity and drag, comparison between our marker's motion in real time and the computational model, and going over some essential questions. So for this experiment, the motion of an object, specifically a crumpled piece of paper, was tracked falling down. Three different position versus time graphs were generated through the tracker, uh, as well as through computational models with only gravity and a computational model with gravity and drag. The goal of the experiment was to determine the effects of gravity and drag on the motion of an object and how it can accurately be predicted. For this lab, you need to know Newton's second law as well as the product rule. And so as you can see here, um, to derive Newton's law, you have to use the product rule and the derivative of the momentum, which it comes from the mass and the velocity. And with the Newton's second law, you can determine the force on an object based on the change in momentum of that object. And with momentum, you can also find velocity and position and other things. So the procedure of this lab, first we recorded the motion of the paper ball falling. Then we imported that video into the tracker's software and tracked the position of the ball at set time intervals. We manipulated the starter code in GlowScript to create two computational models of the ball's motion, as well as creating a position versus time graph based on the data collected. Lastly, we compared the three graphs and models. So in our tracker, the initial velocity was 0 meters per second. Motion was in the negative y direction, and the initial position was negative 0.01 meters. When tracking the movement of the paper ball, I assumed air resistance, outside force, and friction to be negligible, which would theoretically create a constant net force. Time was measured once the ball started moving and was stopped after it reached 0.7 meters. For our computational model, we plugged in zero drag force, the weight force of the paper ball, and also used the velocity update and position update formulas to be able to track the velocity and position. The model with the drag had the drag equation negative bv squared j, and also included b in the initial conditions. So in comparing the models, you notice that they start similar at the beginning, but towards the end, the model with both gravity and drag is closer to the observed model. And this can be caused, or the irregularities in the observed can be caused by shifts in center of mass as well as the movement of the x-axis. So, what do these results mean? Measuring for dp dt, assume that net forces were equal and then deducted the F net from there. And so dp dt can be determined from the slope of these graphs right here. And as you see, dp dt is actually changing, which is, well, actually dp dt is the net force, and the net force is the second derivative of these graphs. So as you can see, the predicted position with gravity is going down with a constant second derivative, while the other two begin to straighten out and have no F net towards the end. We see that terminal velocity in both the simulation and the real life with drag as the graph starts to straighten out towards the end. Um, Now, if the object was thrown downward, it would still have the same terminal velocity, due to the fact that the terminal velocity is determined by the object and the shape of the object, as well as drag, not the initial velocity.